Okay, so this is the second video for the finite square well. And so what did we see in the first video? We started solving the case for negative energy, and we started talking about the even solution of Schrödinger's time-independent equation. So let's quickly review the potential. The finite square well potential. Let's write it here. Finite square well potential is such that it is 0 up to minus a, from minus infinity up to minus a. Then it's some negative value minus v naught between minus a, and then it goes 0 all the way to infinity. And we said, because this potential is symmetric, because this potential is an even function, it splits, it has two solutions, an even solution and an odd solution. The even solution we already wrote in the video in the first part. We said that the even solution is for x larger than a, we have this exponential decay. Now this is prohibited, classically prohibited region, so this exponential decay guarantees that the function can be normalized. Now, instead of giving the solution between minus a and a, we only bother writing the equation between 0 and a. And this equation, we only pick, is the bounded solution, but we only pick the even part of it, and the even part of it is the cosine. And then for everything below 0, we don't need to do anything. The solution is even, so it's just psi of minus x is equal to psi of x. So we went all the way to this point. And we said, this is very nice, this is very convenient, very useful, not to write just this even solution, because now that we are going to be applying the boundary conditions, we only need to think about the boundary between these two parts. We only need to think about the boundaries at x equal to a. So we only need to stitch the function and the derivative of the function at a, instead of doing at a and minus a. So this is very convenient. Now, instead of playing with 4 equations, we will play with just 2. So if you remember this, if you remember that the potential is an even function, this simplifies things a lot. And so we solve everything for the even solution, and then later we solve everything for the odd solution. The odd solution is solved in one of the problems, the problem is 2.29. Okay, so let's now go for the boundary conditions. And so what are these boundary conditions that will allow us to find? We have many unknowns in that solution. We have F, we have G, we have kappa and L. Well, don't forget, kappa and L, they are both related to energy. So what we really have in that solution as unknown is F, D, and energy. Okay, so let's go for the boundary conditions. The first one, as we know, is that the function is continuous. So it is continuous at that position x equal to a. And so that means the two lines that we wrote there, the one involving the exponential, the one involving the cosine, they have to get stitched at a. In other words, that function for x larger than a, at a, so f exponential minus kappa a, this has to be equal to the function for x smaller than a, which is d cosine L at a. Okay, so this is one of the boundary conditions. We are stitching the function at a. The other condition is that also the derivative of the function is continuous at A. This is not true. The derivative is not continuous only in those cases where the potential becomes infinity. But this is not the case here. No, this was the case for the delta function potential, but not here. So let's do this derivative. So the derivative of the part for x larger than a, well, is that f. The derivative gives that minus kappa. And then we have the function exponential minus kappa at a. All right, and on the other side, we have the cosine. So we have the derivative of the cosine gives us minus, and the L, and then the derivative of the cosine is sine, L, and we are stitching at A. Very good. Okay, so what can we do with these two equations? What can we find? Well, first let's simplify this equation, the one involved in the derivative, because there is a minus here and a minus here, so this is gone. And now let me write these two equations, one on top of the other, to make things really explicit. I'm going to start writing that equation for the second condition, which is kappa f exponential minus kappa a equal to L d sine LA. Yes, so I wrote this equation here. Now let me write the other one below, and we have f minus exponential minus kappa a equal to d cosine LA. So I wanted to put both together because you see, they, they look very similar, no? They have some elements in common. And if I get rid of f and g, then we will have an equation that involves only kappa and L. Kappa and L is energy. So if I manage to get rid of f and g, I'll have an equation for energy. I will have an equation that will give us the allowed energies of the problem. Okay, so how can we get rid of f and d? Well, look, if we divide the top by the bottom, we will get rid of f and d, won't we? If we divide the top by the bottom, f disappears, this exponential disappears, d disappears. So what we survive is kappa on the left side. On the right side, we have L. And what is sine divided by cosine? It's tangent. So you see, we got, very nice, we got an equation that will give us energy. So this is very nice. Well, it's true that it's not a very simple equation. It's involving tangent. Now, this is what we call a transcendental equation. Not easy to solve. Well, we can solve it numerically, but can we get any kind of information? Can we go a little bit beyond just a numerical solutions? And we can. But we have to manipulate this equation a little bit because as it is, we have kappa on one side, L on the other side. I know they're all related to energy, but can we do a better job in writing this equation so that perhaps we can do some approximations? That's what we are after now. Well, to rewrite this equation in a nicer form, now I really know where I'm going, okay? But what is the idea? Let's write what kappa was. We have kappa from the previous video, and I'm going to write kappa squared because we saw that there was a minus sign to ME, energy, and h bar squared. So you see, that's why I said kappa is energy. Everything else is just constants. And what was L? Let me also write L squared. L squared did not involve the minus sign, but it was 2ME plus V naught h bar squared. So you see, they also have something similar. But anyway, Kappa and L is energy. All the rest that you see in kappa and L is just constants that are coming for the specific problem that we are dealing with. Like M is the mass of the particle, V naught is the depth of the potential, no? H bar. And so these are all constants. Well, let me try to write one in terms of the other. Okay, so what I'm trying to say is in this equation here, we had kappa and L. Let me try to write this equation just in terms of one of them. So I'll try to write this whole equation just in terms of L. Well, let me continue with this L square. So this L square is 2me over h bar square plus 2m v naught h bar square. Correct. Well, and this is kappa square with a minus sign. Okay, so I'm going to isolate this kappa square because I want to come back to our equation and write my whole equation just in terms of L to make it look much nicer and try to get some approximate solutions, and you will see how. But let's continue here. So what I'm doing from here is writing kappa square. I'm passing this minus kappa square to the left, so it becomes plus. And now I'm passing this L square to the right, so it becomes minus. And the whole thing that we have there, 2m v naught h bar squared, this is just a constant. And now I'm going to bring this to our equation. Well, to bring this to our equation, let me square that equation because I'm playing here with kappa square, isn't it? So I'm going to square that equation. So, okay, so let me bring this equation down here and I'm squaring everything. So I have kappa square equal to L square tangent square, LA. And I'm putting this kappa square here. So my equation now became minus L square, a whole bunch of constants, 2mv naught h bar square, equal to L square tangent square LA. So that's what I wanted. No? So now I only see L as my unknown. The rest is just a whole bunch of constants. Although there is still one thing that is bothering me, because here we have LA, while here I have just L square, L square. So you know what? I'm going to multiply this whole equation by a square. A square, a square, a square. You know why? Because now what do we have? Let me rearrange this. We have, let me go like this. Let me start by writing this one in front. Okay, so now what we have? LA square, tangent square, LA, equal to 2mv naught a square h bar square. This is just a constant. And finally, minus LA square. See? So now I have my unknown is this LA, LA, LA. This is the unknown of this equation. Okay, and so instead of keep writing LA, I'm going to call it Z. Okay, so instead of calling LA, I'll call it Z, so that my equation is Z square tangent square of Z equals to, well, look, as we said, this whole thing is just a constant. And so instead of keep writing m v naught a square, I'll call it just z naught square. This is a constant. So z naught square minus z square. Okay, so this is the equation that I have. My unknown, the variable here is z. Well, let me improve it a little bit more. I'm passing that z square to the right. So I have z0 divided by z, all that square minus 1. And let me do square root. So I have tangent of z equal to z naught divided by z, all that square minus 1. Excellent. This is our transcendental equation that once solved will give us Z. And what is Z? Energy. Okay, so this is the equation that will give us the allowed energies for this problem. It is true, it is a transcendental equation. We can solve it numerically, it's true, but there are some special cases that we can still solve approximately. Okay, well, what does it mean to solve an equation like that? That means we are going to find where the left side crosses the right side. These are the solutions. Okay, so what I'm going to start doing here is first get some space here. I'm going to try to make plots of that, of those two parts, the left side of the equation and the right side of the equation, okay? To try to see where they cross. So the left side is a tangent. We know that tangent, so let's remind us, tangent is sine divided by cosine. And the tangent has some special values at minus pi over 2, at 0, at pi over 2, at pi, at 3 pi over 2, at 2 pi, and so on. Okay, so these are all special points. In which sense? Well, let's start with minus pi. What is sine of minus pi? Sine of minus pi is minus 1. But what is cosine of minus pi? Is 0. Okay, so that means that here, now around this, around minus pi, the function, the tangent explodes on the negative side. Okay, so that's what we are going to put here. It's exploding. And then once we reach 0, well, tangent of 0 is 0. Cosine of 0 is 1. So then we are having to pass here at 0. And then once we reach pi over 2, well, sine of pi over 2 is plus 1. While cosine is 0, so it explodes again, but now on the positive side. Okay. And then as we go on the above pi over 2, we are coming from the negative side. Once we reach pi, sine is 0. And then we explode at 3 pi over 2, and we continue like this. Okay, so this is the tangent. Very good. Now let's try to plot here the other side, the right side. What is this right side? Well, we have there z, so z is here. No? So in that equation, z is in the denominator. So when z is very close to 0, we will have a very large value. And as z increases, so as z increases, since it's in the denominator, this whole function decreases. And so if I have to make a plot, it will be something decaying. Okay, so where does this function meet? Well, when they cross here, when they cross here, when they cross here, these are the solutions, okay, which, as we said, we get numerically. But, as we said, there are some special points. There are two special cases for which we can get more information. And what are they? Well, first case is when Z naught is really large. What does it mean Z naught is really large? Let's go back to our Z naught. And so this is Z naught. If Z naught is really large, that means V, the potential, the V naught is really large. V naught really large means the potential is really deep. A is very large means that the potential is really wide. So let's write this. Z naught large means V naught large, A large. This means very wide, very deep. Well, okay. Well, what is so special about this? If this is really deep, very wide, very deep, very wide, this is making us closer to the infinite square well. Have this in your mind, okay? So physically, that's what it means. But mathematically, if this is not is no, so if this is not is really big, this means that z will have to be enormous for this function to really decay. In other words, if this is not is really big, what we have here, let me bring our functions back here. So if z naught is really big, that function on the right side takes forever to decay, which means the points where they cross will be very close to these points. My drawing is not so good, but very close to these points where the tangent explodes. Okay, so that means that I can say that the solution will be very close to pi over 2. Okay, so the solutions is values of n will be very close to pi over 2. But I have pi over 2, 3 pi over 2, now all these odd numbers. So my solution Zn will be n pi over 2, where n is 1, is 3, is 5, is 7, and so on. Odd numbers. Well, what does this mean? What is Z? Let's go back to what we wrote. Remember that Z is LA, correct? And L is energy. So let's put all this together. So let's remind us Z is LA. So Z square is L square A square, which is this, no? N square, pi square, 2 square. Well, and what is L square? Well, L square is 2m E plus V naught over H bar square equals to N square, pi square, 2 square. No? Well, so then we get a very approximate solution to this energy plus V naught. What is that? N square, pi square, H bar square divided by 2m. We forgot one thing. Oops, there is a square in this story as well. No? So here I have to put this a square. So this a square goes down to the denominator, and we have here 2m a square, and we had also these 2 squares. So we have, I'm talking about, let me mark the two things that I'm putting together. This 2 square and a square. So we have 2a squared. Okay, this is our solution for the energy. Look at that. 4, 1, 3, 5, and so on. Only odd values of n because we need these points. No? We need these points here, pi over 2, 3 pi over 2, 5 pi over 2, and so on. Okay, what do we see here? Wow, this is very similar. It is the solution that we had for the infinite square well. isn't it? Go back to the solution of the infinite square well and confirm that. The only difference is that when we solve the infinite square well, we had the potential between 0 and A. Now we have the potential, that we are writing is between minus A and A. And so we have, it's now twice as broad as this original one. So that's why we are getting here 2A, okay? But the rest is exactly equal to the infinite square well. And we are writing the energy as E plus V naught, because look, if you go back to the infinite square well, let me make a sketch here. The infinite square well was between, it was an infinite wall at 0. I didn't do this well. Let me restart. And so for the infinite square well, we had an infinite wall at 0. The potential was 0 between 0 and A, and another infinite well. Okay, so when we would put a certain value of energy, what we got when we solved the problem was the value of the energy was n squared, pi squared, h bar squared divided by 2ma squared. And so this was this energy above the minimum value of the well. Okay, now what we have for this finite square well, but very, very deep, yeah, we have something, it is 0 here, and then here it's really deep. Yeah, between minus A and A. So this E plus V naught that you see here is what we have above the minimum of the well. Okay, so above the minimum of the well, just as here above the minimum of the well. But the minimum of the well here was 0, while here is this minus V naught. So that's why our solution is E plus V naught. Okay, but you see that, as we said, on the right side, we are having a scenario very similar to an infinite square well, because we are dealing with an extremely deep well. Okay, now you may say, but wait a second. In this solution here for the real infinite square well, we said that n could be 1 and 2, 3 and 4, 5 and 6. While now, where we have an approximately infinite square well, we are just picking the odd numbers. Where are the even ones? What happens to the even ones? Aha! What do you think? The even ones also exist. Let me erase all this. The even ones, erase all this. The even ones also exist, but for the odd solution of the Schrödinger equation, the one that is involving the sign, okay, which is for the problem 2.29 that I mentioned to you. So the odd solutions will give us the same scenario, when the well is very, very deep, the same solution, but now for the odd case, the n will be 2, 4, 6, and so on. Okay, so for the odd case, n is 2, 4, 6. For the even solution that we played with here, we get the odd ends. All right, very good. Now let's discuss just one more case. Just one more case. Let's see if we can come back. Yes, I think we can come back up here. So this one more case is just going to be qualitative, So let me remove this. We are going to talk about one more case. So let me erase this special case that we talked about. Come back. Keep here our tangent. And this second special case, which is we are just going to talk about it, there are no numbers to be given, but is the other extreme, is the case where Z naught is really small, tiny, tiny. So small, né? And what does it mean? That V naught is very small, A is very small. In other words, we have a very shallow and very narrow well. Very shallow, very narrow. So if I would have a look at this potential, something very narrow and very shallow here. Okay, so in a case like this, we almost have nothing. We almost have no solution. And we can see this in our plot. Because if this Z naught is very small, if the Z naught is very small, any Z already decays really fast. So this function decays really fast. And in this case, there is only one single solution. Okay, so when we have this very shallow, very narrow well, we have a single bound state, and that's it. Okay, so this is the end of this video. In the next one, in the part 3, we are going to then finally start talking about the case where the energy is positive. So this is the end of this video.